lecture on higher order linear differential equations with constant coefficients. So we'll go over lesson 20, L20 in your textbook. So first we'll discuss the characteristic polynomial, and it turns out that finding the roots of this characteristic polynomial is how we solve a higher order linear differential equation with constant coefficients. Say an minus 1 all the way to a naught are constants, and a naught, an, the first constant, is non-zero. This equation, an times the nth derivative of the unknown function y plus a minus 1 times the n minus 1 function of the unknown function y plus a minus 2 times the n minus 2 derivative of the unknown function y all the way to a1 times y prime plus a naught times y is equal to 0. This is a homogeneous linear differential equation with constant coefficients of order n. We'll see that the differential equations of the form above have the following solutions: e to the rx, where r is a complex number. Now, if we assume the unknown function has the form e to the rx, its derivative by the chain rule is e to the rx times the derivative of rx, which is just r. The second derivative is r squared e to the rx, and if we take the nth derivative, we get r to the n times e to the rx. Plugging these functions back into a homogeneous linear differential equation with constant coefficients gives the following: an r to the n e to the rx plus a minus 1 r to the n minus 1 e to the rx all the way to a naught. So in this case, we have a factor of e to the rx in each term, and if we factor that out, we get e to the rx, and what's left is y was replaced with r, and the number of times it was differentiated is replaced with the power. N here, and minus 1 here, and just 1 here. R to the 1 is just r. E to the rx is never 0. That's still true when r is a complex number. This means a n r to the n plus a n minus 1 r to the minus 1 plus all the way to a1 r plus a naught is equal to 0. So this is called, what's on the left-hand side here is called the characteristic polynomial, and this is called the characteristic equation corresponding to the differential equation of order n. So each differential equation of linear differential equation of order n with constant coefficients has a corresponding characteristic polynomial. And then it's formed by replacing y with r, and each number of times it's differentiated with that corresponding power in the exponent. So it's actually, because of this, solving this differential equation reduces to setting the characteristic polynomial equal to 0 and solving for r. Equivalently, finding the roots of the characteristic polynomial. Here are 3 cases. There's indistinct real roots of the characteristic polynomial. All roots of the characteristic polynomial are real, but they repeat. Or all roots of the characteristic polynomial are imaginary. Suppose R1 to Rn are indistinct real roots of a characteristic polynomial. In that case, now notice these roots usually are found by either factor or using quadratic formula. In that case, we just say e to the r1x, these e to the r2x, e to the r3x, and e to the rnx. We get linearly independent functions of this differential equation. So that's pretty straightforward. Just take each of the roots, put them in the exponent for e to the power e to the r1x, e to the r2x, all the way up to e to the rnx, and we get n linearly independent solutions. And then just take a linear combination, we get our n-parameter family of solutions that was promised in the existence theorem. So notice this differential equation will always have an n-parameter family of solutions. That is an n-parameter family of solutions that's formed by linearly independent functions and taking a linear combination of those. So here's an example for when we have distinct roots. Let's look at this second order differential equation, y double prime minus 7y prime plus 10y is 0. The associated characteristic polynomial is r squared minus 7r plus 10. We can factor this polynomial into r minus 2 times r minus 5. This means the roots are 2 and 5. So voila, we get e to the 2x and e to the 5x as the two linearly independent solutions of this second order linear differential equation. And we just take any linear combination of them, c1 times e to the 2x plus c2 e to the 5x, and we get a two-parameter family of solutions. Now let's look at something else that can happen, like case 2, where we don't have two distinct roots, we only have one repeated root. Y double prime minus 2y prime plus 1 is 0. This characteristic polynomial is r squared minus 2r plus 1, r minus 1 squared. The only root of this polynomial is r is equal to 1. This is a repeated root. So if y1 of x e to the rx is a solution of y double prime minus 2y prime plus 1 is equal to 0. So notice it's always the case. You can always get a solution. Once you have a root of the characteristic polynomial, you can always form a solution just by taking e to the rx. It's true whether or not r is real or complex. In this case, it's real, and we get e to the x is a solution. But this is just one solution. You need another one, right? Because it was promised that if we have a second order differential equation, there was a theorem that said we get two linearly independent solutions. So let's try to find the second one by multiplying the given solution by a function u of x, an unknown function u. In this case, its first derivative is u prime plus u times e to the x. Its second derivative is u prime double prime plus 2u prime plus u times e to the x. If we plug y double prime minus 2y prime plus y is equal to 0, this gives the following. U double prime plus 2 u prime plus u minus, 2 in parentheses u prime minus u plus u. Well, what we get here is, I'm sorry, this should have been minus 2u prime plus u, but what we're left with is u double prime times e to the x. That means u double prime is 0. If u double prime is 0, then u of x is the function constant plus a constant times x. You notice if it was just a constant, right, then we'd get a constant times e to the x. Well, that's just this family, one parameter family of solutions, a constant times e to the x. We already saw that. The new linearly independent solution that here pops up here is x times e to the x. And just looking, so what we can conclude is that c1 times e to the x plus c2 times this second, we can check that e to the x and x e to the x are both linearly independent functions, and their linear combination forms a two-parameter family of solutions. So let's consider the, so that was case 2. Now let's move on to case 3. Consider this differential equation. Y double prime plus y is 0. In this case, the characteristic polynomial is r squared plus 1. If the characteristic polynomial is 0, r squared plus 1 is 0, or r squared is negative 1. This means that the roots of the characteristic polynomial are I and minus I, and y1 of x is e to the ix cosine x plus I times sine x, and y2 of x is e to the minus x cosine x minus I sine of x. These are two linearly independent solutions, and these are complex values. So normally, especially in physical and engineering applications of ordinary differential equations, we want our solutions to be real valued because those represent things we can measure. So in this case, we can take these two linear combinations, 1/2 y1 plus y2 to get cosine, 1 over 2i y1 minus y2 we get sine. These are real valued solutions, and if we restrict ourselves to real valued solutions, we get the following two-parameter family of solutions to y double prime plus y is equal to 0. This will become important later on when we study motions of springs. So c1 times cosine x plus c2 times sine x is a two-parameter family of solutions to y double prime plus y is equal to 0. Okay, so that's really the three cases that we'll go over now, and you'll see in your homework. We will be seeing more cases later on when, it's also possible for us to have, say, complex valued roots of the characteristic polynomial. In that case, our solutions are going to look like e to a power times x times cosine x plus e to the power times x times sine x. So we'll see that later on, probably in Wednesday's lecture.